Let's get back to work. I received some feedback telling me that it's not really clear what I write, and it's a bit chaotic, and I know, I'm aware of it, but as I said, the purpose of these videos is not actually to teach, but just to practice. However, I will take it into account and make an effort to improve on this. Se me tapó el mate, loco. Okay, so we have seen how to derive the distribution of a sum of two random variables, and now we will switch to tail sigma algebra. Tail sigma algebra, so consider this thing here, script Tn as the sigma algebra generated by the union for n greater than m of the sub-sigma algebras Gm, which we denote more simply in this way: big V n greater than m of Gm. This thing here is the information about the future after m. So basically this is the sigma algebra generated by the union of Gm when n is greater than m. When m is greater than n. Yeah, I was thinking about it. So basically, I will try to make a graphical example for this. Consider something like this. We have some kind of random phenomena, and well, here is time 1, time 2, time n, and time m, which is greater than m greater than n, and basically we have this thing here is f1, well, in this case g, let's call it g1. Up to here we know the information g2. Up to here we know the information gn. And here we know the information gn. This dn is the information about the future after time m. So basically this thing here is Tn, which is the sigma algebra generated by all times after n. So we have like this, and we have, let's say, m2, m3, etc. And so we consider all these times, we take the union of those, and this gives as result this sigma algebra. And now given this, we can define the tail sigma algebra, which is this thing here. We denote it with the calligraphic. I will just write it like this, but it's still a T. And this is the information about the remote future. So it's something which happens really at the end of the process, and it should be the intersection. Since we consider all these times, we take the intersection. So this is greater, we take, like, let's say this is the information after m, then we take this one, we take this one, we take this one, and the intersection of them becomes smaller and smaller, because the intersection, as you remember, it's the set of all m elements which are common to all of them. So it becomes smaller and smaller up to some point, which we will have this t here. So this is the intersection over m greater than n of what? Of gm, I guess. No, it's actually the intersection of all these tn, of all these things here. And this is the tail sigma algebra, and it's the information about the remote future. So it is quite counterintuitive, because this sigma algebra is considering all the events which happen very late in time. It's like kind of reversing time, or reversing the point of view in which we study the process. Maybe it's more appropriate. And this has the following heuristic interpretation. Heuristic interpretation. Oops. The tail sigma algebra T includes all events which are not affected by what happens in finite times. So basically what happens here doesn't have any kind of consequence on what happens in the remote future. So all this thing does not have, like everything which we have in early times, doesn't change the behavior of the process in the long term, let's say. We can give this other interpretation as well. So let's make some examples. Consider xn with n in the natural numbers. I will skip it, where this should be written in this way, but I will just skip this. I will just write this. And gn, which is an increasing set or family of sigma algebras, which is the sigma algebra generated by the xn, and consider Sn to be the sum of the xn. Well, let's call xi for I from 1 to n. Okay, so we have the following examples and non-examples. The first one is this: the set of outcomes such that the limit of Sn, the limit over n of Sn of omega exists. So this is a sum of random variables. For example, 1, 2, etc. We can, for example, consider normal random variables. We start from some random point here. We have an initial distribution. Here we have another random variable. Let's put it like this. And here we have another one with another distribution. I mean, oof. Okay. So let's say the process evolves in this way. So this is x0, this is x1, well, this is x1, this is x2, and we have that this thing here, the final result. Well, this is s2, this is s0, this point here is s0, this is s1, this point here. So we sum the result of these random variables, and now we want to know if the limit of this process exists. But to know if the limit in the long term exists, we need to know the information of what happens in the remote future. And so this event belongs to the sigma algebra script T. So this is a tail event. We call it a tail event when it's an event that belongs to the sigma algebra, to the tail sigma algebra. Well, this process may go down, up, blah blah blah, something like this. So now, second example. Here it says take a Borel set B in the Borel sigma algebra. And consider the event the following one: the event of outcomes such that xn of omega belongs to this Borel set infinitely often. So the realization xn of omega falls into this set infinitely often, which means infinitely many times. And this can be also written in the following alternative way: omega is the indicator on the set B. Well, it's the sum of the indicators. It's the sum over n of the indicators over the set B of xn of omega. And this thing is, oops, this sum goes to infinity, because since it happens infinitely many times, we basically count how many times xn falls into the set B. When xn is in B, we add 1. When xn of omega is in B, plus 1. And this thing here is also a tail event. Why? Because in order to diverge, it can only diverge if we consider an infinite amount of time, I guess. Here the situation is something like this. We have, let's say, x0, and let's say B is this set here. Let's say it goes like this is x1, x2, x3, and then okay, and then it goes like this, x4, so it falls into the set, and here we have a plus 1, so here we start counting, maybe it goes outside, but in the long term, when we consider the entire history of the process, we will have that considering an infinite span of time, the number of times, so here 1, here 2, bam, 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 we sum of all of them, and this sum goes to infinity, which can only happen if we consider the tails in algebra, I think. And this, in particular, can be related, I think, to the number of upcrossing, and yeah. That we will see in the final part of the course about martingales. Let's go with the following example. Oops. Well, I can do this and this. Okay. No problem. I wanted just to write a dot here. Okay, let's go with the third example, which is this one. It's the set of outcomes such that Sn of omega falls into the set B infinitely often. This thing is not a tail event. Why? Because, for example, if we consider B to be the set 0, so simply the point 0, so that this becomes the set of outcomes such that Sn of omega is 0 infinitely often, and we call this A, we consider xn such that the probability that x1 is 1 is p, and the probability that x1 is minus 1 is 1 minus p, with p in 0, 1, then we have that x of omega, or the sequence, will be plus 1, minus 1, plus 1, minus 1, and so on. For this omega. Okay, so for this omega. So for this omega is in A, but for x of omega tilde, which can be plus 1, and then again plus 1, minus 1, plus 1, minus 1, plus 1, blah, blah, blah. For this, we have that omega tilde does not fall into the set A infinitely often, because graphically what we would have is that for omega tilde we have, let's say, we start from 0, we have plus 1, we have plus 1, and this is let's say A. So this is the set A. We are interested in the number of times in which it falls into this thing here, and then we have basically like this, so it never touches this thing. So from this we get this. So A does not belong to the sigma algebra generated by the x3, x4, x5, etc. and so on, which we could alternatively see as the 1, 2, 3, maybe G3, so the information about the future after time 3, and this does so A does not belong to it. I don't really know if this kind of notation is appropriate. Well, here it says T2, and from this it says that A does not belong to T. Oops, to T. We have some other examples. I think there are 3 more. Let's go. Let's continue with the 4th example. Let me cancel here. 4th example. which is the following. Is the set of outcomes such that the Sn of omega over n is finite. And this thing belongs to the Tail sigma algebra. What is this thing? This is the sum of the random variables over n, which is the average, and the average is finite. And we can know that the average is finite only if we consider all the time up to infinity. Or if you want, if we change the first n random variables, the mean does not explode. Okay, so to see why, define Z1 to be the limit inferior for n going to infinity of what? Of Sn over n. And Z2 to be the lim sup of the same quantity for n going to infinity of Sn over n. So that this set becomes the set of outcomes such that the limit over n of z, well, basically the limit such that z1 is equal to z2. And to see that this is in T, rewrite Sn over n in the following way. Sn over n is 1 over n, the sum of xi plus, okay. Consider m. Let's do this thing here. 1 over m, the sum from 1 to m of xi plus 1 over n, the sum from 1 to n of xi. So we split, here it's m plus 1. I equal m plus 1 of xi. Oops. Here is an n. So we split this sum into the first m variables and into the second part, starting from m plus 1. Like, for example, if we have x1, x2, x3, and so on, xm, then we have xm plus 1, and so on, xn. We simply split this here. We consider this sum. Well, let's put it like this. This thing here is this thing, and this thing here is this thing. But this thing is finite. Oh, okay, wait, oh, okay. This thing is n, here we have n. Oops. Here it's not an m, it's an n. So this goes to 0 as n goes to infinity. And so well, we can call this thing as Sn1 plus Sn2, which are basically these two sums, but this thing goes to 0, and well, m is less than n. And here, I don't know why, but this concludes in this way, saying that therefore the set in which z1 is equal to z2 belongs to D, script D. Opa. Why? Because this is basically, I don't know, it's quite similar to the example in which we saw that the limit exists, I think. Okay. Well, let's recap the 4 examples of events which are in the Tail sigma algebra. The first one is that the limit of Sn exists. The second one is that for B in the Borel sigma algebra, the outcomes such that xn of omega falls into B infinitely often. This is a tail event, this is a tail event. Thirdly, this set in the event in which the outcomes, the set of outcomes such that Sn omega falls into B infinitely often, this we have seen that does not belong to T. And finally, what we have seen now, what have we seen now? We saw the set of outcomes such that the average is finite. And this thing is a tail event. And now, why it's important to know if an event does or does not belong to the Tail sigma algebra? Because the following theorem will tell us something interesting about this, and this. And let me write it here. Theorem Kolmogorov-01 law, which says that given G1, Gn subsigma algebras of H, which are independent, or formal independence if you want, then the probability of an event H is either 0 or 1 for any H belonging to the Tail sigma algebra. So, if the sigma algebras are independent, the probability of this event here, this event here, and this event here will be either 0 or 1. So, either the limit will exist or it will not. Either the realizations of the process will hit a set infinitely many times or not, and we will have that the mean of the process will be finite with probability 0 or 1. So when we have independence, the Tail sigma algebra is composed by almost sure or almost impossible events. Almost sure when the probability is 1, almost impossible when it's 0. The proof of this simply relies basically on one observation and to a repeated use of a previous result that we mentioned, which is the fact that in a partition of an independency is again an independency. So consider, okay, we have that G1 and so on, Gn, Tn, Gnt, script T is an independency for any n. And since Tn is contained in T, or T is contained in Tn, T is contained in Tn, for any n, we have that this partition here, Gn Tn, is again an independency. And now again, we can write it like this: the G1, G2, and so on is again an independency. Why do we write it in this way? Here it's simply T. I'm making some confusion here. This maybe should be Tn, yes. And since then we have that this, okay. And we rewrite it in this way, and now we can call, from this we can actually group all these things together and write it as T0, which is again an independency. And now consider H in T and G in T0. G in T0. Since they belong to sigma algebras that are independent, so since T is independent, let's write it like this from T0, we have that the probability of H union G factorizes into the product of H and G. Tapadísimo. And now what can we say? What can we conclude? I don't remember. And here it says that since T is contained in Tn, for any n, and T is contained in T0, then T is contained in T0. And why is this important? This has something to do with this, but I don't really know what is the thing. But in any case, if we let HPG or G equal H, what we get is that the probability of H is the probability of H with probability of H. And this can only be the case if probability of H is either 0 or 1. The proof is not so long and it's not so complicated, but I should practice it a bit more. punto. Let's now leave the notion of independence and tail events, tail sigma algebras, and start talking about convergence. And for this, we first recall some notions or results of convergence from real analysis. Okay, let Xn be a sequence of real numbers, where n is in the set of positive natural numbers. Then the lim-inf over n of Xn is defined as the supremum over n of the infimum, where n is greater than m of Xn, and the lim sup, the limit superior, over n of Xn of this sequence is the infimum over m of the supremum for n larger than m of Xn. So these are the definitions of lim sup and lim-inf. If we have basically the lim-inf is the limit of the infimum of a sequence, and the lim sup is the limit of the supremum. So if we have, for example, a function like this, bam, 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 bam. Okay, let's say the supremum is the largest while the infimum is the smallest. Okay, and for example here the lim sup goes like this, so this is the sup, this is the inf. Well, but actually here in this case, this is still the inf when we consider after this time. For example, this is the new infimum. We consider after this time, this is the new infimum. And we consider it and we analyze the limit. So for n, here we have n, we let n go to infinity. Let's try to make a clearer example. So 1, 2, 3, 4, 5. And let's consider this sequence here. So this is x1, x2, x3, well, this is x0. Let's not even count it. x1, x2, x3, x4, and x5. This is the infimum up to here, this is the supremum, and for example, up to some point, let's say we consider this as threshold m, the lim-inf is the supremum of the infimum. For n larger than m. So this is n is 5, n equal 5, larger than m. Let's say m is 3, m equal 3. So this is the supremum of the infimum. The supremum over m, infimum. I don't fully understand this. In any case, if the limit of xn is equal to the lim sup of xn, we say that the limit of xn exists. So basically these two things become the same thing at some point. Okay, and now we have to introduce some notation. We will call I epsilon this thing here, I epsilon of x. The indicator on the interval epsilon plus infinity. Which is 0 when x is smaller than epsilon, and 1 when x is greater than epsilon. So, for example, let's consider a small epsilon here. The indicator is this function here. So for example, if we have a function x, let's put it f of x, the resulting function will be this one here, and here it will be 0. And now we have some remarks. The first one is that the sequence xn of real numbers converges to x, which is again a real number, if and only if the distance between xn and x goes to 0 and then goes to infinity. The second remark is that a sequence xn real numbers which are positive converges to zero if and only if for any epsilon greater than 0 there exists a case such that, well, xn is less than epsilon for any n greater than k. In other words, or in other terms, xn goes to 0 with an increasing if and only if the sum over n of I epsilon of xn does not explode for any epsilon greater than 0. A sequence of positive, for example, so we have all positive numbers converge to 0 if for any epsilon greater than 0, let's say this is epsilon, there exists some k such that there exists some some n greater than k such that for any n greater than k all the xn no such that for well xn is smaller, this is smaller, this is smaller, this is smaller, so they are all smaller than epsilon, which means xn converges to 0 if and only if the sum of indicators, so in this case we consider like this, if a point is here with some 1, if a point is here with some 0, or we simply do not sum anything, so we will have like a finite sum, plus 1, blah blah blah, but up to some point we don't have any contribution, and so if this sum is finite, it means that it converges to 0, because all the others will be smaller than this threshold, which can be as small as we want. I think this can be a quite good interpretation. Another thing that we have is the following. That the sum of the indicators are finite if and only if the lin sup of the indicators is 0, right? which is equivalent to ask that also the remove over n of the indicators xn is 0. Correct. Nice. So this is a quite, I don't know where we will use this thing, and I don't remember where. Oh, okay. This we will use it for almost sure convergence, for the characterization theorem of almost sure convergence. Okay. And one final thing is the Cauchy criterion. Which says basically the Cauchy criterion allows us to see or to assess whether a sequence converges without knowing its limit. And more formally, we can put it in this way: a sequence of real numbers xn converges to x, which is again a real number, if and only if the limit as m and n go to infinity of this distance here is 0 for any m greater than n. So basically we look at how can we describe this? So basically, as the terms of there is some point up to which all the terms in the sequence are very close together, I think. And now we have a proposition which says that if there exists a positive sequence epsilon n such that the sum of the terms of this sequence is finite, and the sum over n of I epsilon of this thing here, xn plus 1 minus xn, converges, then the sequence is converging. How to interpret this? And where do we use this? So if there exists a sequence of numbers which is converging, and the sum of the indicator of this thing converges, then the sequence xn converges. Now let's go with another proposition, which is called selection principle. If every subsequence that has a limit has the same limit value x, then the sequence tends to the same limit. Let's try to write it formally. If every subsequence xk, xnk, nk converging to x, well, converges to the same limit x, then the sequence tends to the same limit. Then the sequence xn tends to the same limit. And if the sequence is bounded and every converging subsequence has the same limit x, then the sequence converges to x. So if the sequence is bounded, if the sequence xn is bounded, and every convergent subsequence has the same limit x, then the sequence converges to x. Now, I don't know why we should add even this if we just have this, which is the same as this thing above. But maybe I just wrote it badly. And this thing will be used in the relationship between convergence in probability and almost sure convergence. Now we have a lemma about the behavior of lim sup. Behavior of lim sup and lim imp. let xn be a sequence of positive real numbers and xn bar be the average. So the sum from 1 to n of xn over n. And let n be what? A subsequence of n. Okay, and k, let's put k also here, subsequence of the natural numbers. This is different. Note, these are different. Here we have n, here we have the set of natural numbers. Okay. With limit over k, nk plus 1, nk plus 1 over nk, nk, which is equal to r, which is positive. Now, if the sequence xn bar converges along n, and it's not along the set of natural numbers but just capital N, to x, then we have this thing here, x over r. X over r is bounded above by the lim inf of xn bar, which is in turn bounded above by r tan x. So if we have a sequence of positive real numbers, we define its average, and we have that if a subsequence which has this particular limit here, then if the average converges, we have this expression here. My question is, where do we use this? I think we use this in the following theorem. Kelly. So this theorem is named after Kelly, and it says the following: for every sequence Cn of distributions, of distribution functions, there exists a subsequence Bn and a limiting distribution function C such that the limit for n going to infinity of Pn of t is C of t for any t at which C is continuous. So this is somehow related to convergence in distribution. If we have a sequence of distribution functions, there is a subsequence and a limit in distribution function such that the limit of the subsequence is the distribution function. Where do we use this? I don't know. Now, one remark that we have about the previous lemma is that the lemma that we saw, this thing, gives an idea about the fluctuations of a sequence of averages in terms of the subsequence n and the limit x. Okay. And we have another lemma now. Okay, which is named after Kronecker. Kronecker, which is the same Kronecker of the delta of Kronecker. The Kronecker lemma says that if we have a sequence of xn of real numbers, strictly positive and increasing to infinity, and we have a sequence an positive and increasing to infinity, and yn, which is the sum for k from 1 to n of xn over ak, if yn converges, then the limit for n going to infinity of 1 over ak, the sum of xk, goes to 0. Let's try to read it again. So if we have a sequence in R and we have a positive and increasing sequence, and we define yn in this way, if we find out that yn converges, then the limit of this thing goes to 0. So these were all the results of real analysis that we need for the following section, which will be about the convergence, different types of convergence, which is the most important part of the course. And for this, I think it is appropriate to take a break now. and we will see next time.